All right, guys. So at this point, we've covered everything we need to. We're ready for our first significance test. We've talked about the basics of how hypotheses work. We've talked about when do we know when to reject or fail to reject a null hypothesis. And we now know also about the potential errors that can occur when we either reject or fail to reject a null hypothesis when maybe we should or should not have. So we're going to first talk about how to do tests for a population proportion. To begin with, let's make sure we understand what conditions we need to have met. By the way, these are the same conditions that we used for confidence intervals for a proportion, so kind of a nice thing that we don't have to relearn some of this stuff. But just as a friendly reminder what those conditions are, the first being randomness. We have to make sure the data comes from a well-designed experiment or random sample. Next, 10% condition, we have to make sure that 10 times our sample size is less than or equal to our population size. As a reminder, that's what we use to check for independence. It's also what's necessary in order to calculate our standard deviation. And then last but not least is large counts. That's going to be n times p null needs to be greater than or equal to 10, and n times 1 minus p null also needs to be greater than or equal to 10. Remember, that's what we use in order to establish that it is a approximately normal sampling distribution. And notice that we're using p null. What that is the claimed proportion from our null hypothesis. So just to make sure we understand, this is not the one that we actually get from our sample, but what is actually being claimed. So let's go ahead and talk about a few other things with significance tests and kind of the basics of kind of what they do. So a significance test is basically where we're using sample data to determine whether or not we have enough evidence against our null hypothesis in favor of whatever our alternative is. So some basic principles that apply to those tests. First being that a test compares our statistic from our value with our parameter of the null hypothesis. Number two, when we have statistics that are really far away from our null hypothesis value, we are going to have stronger evidence against our null hypothesis. And then last but not least, to assess how far it is, we're going to standardize our statistic using what's called a test statistic. And in parentheses, I've mentioned that is what we would refer to as a z-score. So a test statistic measures exactly how far a sample statistic is from our claimed population parameter when we take variability into account. So in order to calculate it, and by the way, this formula is on your formula card, we take our statistic minus our parameter divided by our standard deviation of the statistic. Now, what that should sound a whole lot like is what we mentioned up here, a z-score. So if you think about how it is we calculate z-scores, a z-score we always found by taking our value p hat in this case minus our claimed proportion p null divided by our standard deviation or our standard error of our statistic p null. So we'll talk about how to calculate that here in just a little bit. Let's make sure we understand what steps we're going to have to take in order to perform our one sample z-test for a proportion in this case. So you'll notice that there are 4 steps here. It is our 4-step process that hopefully we are still familiar with, which is the state, plan, do, and conclude. You'll notice that each of those has 2 parts to it, and those 2 parts represent 2 points. And so if this was a quiz or test question and I asked you to build a one sample z-test for proportion, there would be 8 points for that particular problem. So let's talk about what those are. In your statement, there are 2 things you need to include. One is your parameter of interest. The other are your hypotheses. These are both your null and alternative hypotheses, as well as your significance level alpha. Now, off to the side here, I want to make sure we understand that we are going to assume that our significance level is 0.05 if it's not otherwise stated in the problem. Sometimes it'll tell you use a 1% significance level, and if that's the case, use alpha as 0.01. Otherwise, assume 0.05 if it's not otherwise stated. Next thing we're going to do is in our plan, we're going to state what inference method is going to be used. In this case, that's a one proportion z-test. In the future, we'll have one sample z-tests and so on and so forth. Also in our plan step, let me not forget this, we need to check all our conditions are met. So make sure it's random, make sure it meets 10%, make sure it meets large counts. Next is our do step. So in our do step, we're going to actually find our test statistic, which is z, and find our p-value, which we'll use normal CDF to find. In our conclusion, we're going to make a conclusion about our null hypothesis first, whether we reject or fail to reject, and then make sure we do that in context second. So there are the 8 things that you need to do for each of these problems for a one proportion z test. Last but not least, let's talk about how to find that test statistic z. In order to calculate z, we're going to take p hat minus our p null divided by the square root of p null times 1 minus p null over n. Okay. So what happens if our data doesn't support our alternative hypothesis? Like, let's say, for example, for our null hypothesis, we're assuming that it's going to be a proportion equal to 50%, so p null would be equal to 0.5. And then let's say for our alternative hypothesis that our proportion we believe is going to be actually greater than 0.5. And then let's say when we conduct our sample, we end up with a p hat, which is equal to 0.23, which is in the complete wrong direction from what we picked. We thought it was going to be more, it ended up being less. Then what's going to happen is, without doing any other calculations, we can fail to reject our null hypothesis, and we don't have to show any calculations. We don't have to do any other work. No conditions have to be checked. We can just go straight to failing to reject. So as you can imagine, that won't happen often, but in the case that it does, go ahead and just fail to reject and move on. So let's take a look at one example here together in this video. We'll save the next example for class. So according to an article in the San Gabriel Valley Tribune, February 13th of 2003, most people are kissing the, quote, right way. That is, according to the study, the majority of couples prefer to tilt their heads to the right when kissing. In the study, a researcher observed a random sample of 124 kissing couples and found 83 of the 124 of the couples tilted to the right. Is this convincing evidence that couples really do prefer to kiss, quote, the right way? All right, so let's go through that 4-step process. We'll start with our statement. So in our statement, there are, once again, 2 things we need to say. First is we need to say our parameter of interest, which is, in this case, p. What p is going to represent for us is the true proportion of couples who kiss, quote, the right way. Next, let's go ahead and set up our hypothesis. So for our null hypothesis, it says up here that the claim is that most people are kissing the right way. So most would indicate a majority. In other words, that 50% of couples are kissing, quote, the right way. And that's a pretty common thing with proportions. Typically, it will be 50% as a null hypothesis, but sometimes it might be different. For the alternative, we believe that there's actually going to be more couples that kiss the right way. And so we're going to say that our proportion is actually greater than 0.5. And since it doesn't list a significance level for us, we'll go ahead and assume that for our significance level, that 0.05 will be good enough. Okay, so next in our plan, let's go ahead and say what tests we plan to use and check the conditions for it. So our plan is going to be to do a 1 proportion z test. That's going to be the same for all of our proportions. For right now is that single proportion z test. And then let's check our conditions. First of all, is this coming from a random sample or random experiment? And it does say right here that it is a random sample. So yes, we can go ahead and say it satisfies that. Next, let's check our 10% condition. If we take 10 multiplied by 124, we get 1,240. Is it reasonable to assume that there were more than 1,240 couples that we could have sampled from? I would say also yes. Last but not least, let's go ahead and check our our large counts condition. We're going to take our number in our sample, which is 124, multiplied by our claimed proportion p null, which is 0.5. That's going to be equal to 62, which is in fact greater than or equal to 10. And even if we were to do that a second time, keep in mind 1 minus p null in this case would also be 0.05. We would also get 62, and 62 is also greater than or equal to 10. So large counts condition is going to be met. So we can assume that our distribution for the sampling distribution is approximately normal. Okay, so now let's actually do our test. So here's where we need to calculate a couple of things. First thing we need to calculate is our test statistic, which is z. To find our test statistic, we're going to take our p hat, which is 83 out of 124, minus our claim proportion, p null, which is 0.5, and divide that by the square root of our standard error here. So 0.5 for p null, 1 minus 0.5 is also 0.5, all over our square root of n, so 124 there. Okay, so let's grab a calculator and let's be careful with how we type this in. So first of all, 83 divided by 124, and then divided or minus 0.5 first. I'll do this in kind of a couple stages. There is the numerator for my fraction, so approximately 0.169. Over, let's calculate our denominator now. So the square root of 0.5 multiplied by 0.5 over 124 is going to give us approximately 0.449. And then now dividing those two, we should get our test statistic. So take our first decimal divided by our second, and we come up with a test statistic of approximately 3.77. Next, let's go ahead and find our p-value. So for our p-value, we're going to be using normal CDF in order to find that. So keep in mind, for normal CDF, our lower is going to be the actual value from our sample. So the 83 out of 124. We'll pick something infinitely large for our upper. And then for our mean, we'll go ahead and use 0.5 for that. And then standard deviation would be basically what we found right here in our denominator of our fraction. So 0.0449. And we'll try to use that full decimal as well. Okay, so let's go ahead and use normal CDF to find this p-value. So we'll go into our distributions menu. We'll choose normal CDF. For our lower, here is that 83 out of 124. For the upper, pick something very large. Mean, 0.5. Standard deviation, I've got it typed in here. The square root of, I went ahead and simplified 0.5 times 0.5 to be 0.25 over 124. And when you're ready, go ahead and hit paste and hit enter. So we've got 8.109 multiplied by 10 to the negative fifth power. So I suppose if you really like to see what the actual decimal is, just move that 5 places to the left. And here is your p-value as a regular old decimal. In other words, 0.00008109. Okay. Last but not least, let's go ahead and write our conclusion now. So based on our p-value, we're going to say that because our p-value, and make sure to actually say what the p-value is. So I'll just say 8.109 times 10 to the negative fifth power is less than our significance level, which again, make sure to include 0.00 or 0.05 there. We are going to reject our null hypothesis. In other words, there is convincing evidence towards our alternative, but let's make sure we put that in context. So there is convincing evidence that the true proportion of adults, and in this case couples, so adult couples, kiss, quote, the right way. All right, guys, so there is kind of your all 4 steps worked out for how to do a 1 proportion Z test. We'll do one more, like I said, with that other example next time we meet in class. Until then, have a good rest of your day.